the name of Almighty God, I am Mahsa Sankoshi, and today I want to talk about free streaming regime. In order to proceed with the narration, we need to consider next what happens after recombination. In the regime where photons free stream, for that we go back to the equation 1.19, which we can rearrange as theta prime minus I ca micro minus tau prime multiplied by theta is equal to S, with the source function s defined as s is equal to minus I ca microphi minus tau prime theta is 0. To get here, we have moved to conformal time, neglected for the moment the time dependence of the gravitational potentials, and neglected nu BK, the dipole of the baryonic matter density. We then find the solution of equation 1.31 in conformal time and expand it in legendary polynomials, which causes the spherical Basel function JL appear. We finally get C, the reference theta 1, to the following result, which provides the values of the multiples of the photon field at the present day. For example, at eta 0. Theta L is multiplied by K, and eta 0 is equal to the integral. The lower boundary is 0, the upper boundary is eta 0, d eta, g eta, and theta is 0 K eta plus phi K eta multiplied by JL K eta is 0 minus eta. Here the visibility function g eta is equal to minus eta prime a tau prime exponential minus tau eta gives the probability for a photon to last scatter at conformal time eta. It is picked at the eta is equal to eta recombination. For eta where is less than the eta recombination, it is too much less than the eta recombination. It is very unlikely that the photon would not continue to scatter in the tightly cooped photon baryon fluid, while for eta is more larger than eta recombination, the universe is transparent. Thus, in both limits, g eta tends to 0, and to a good approximation, we have theta L K eta 0 is equal to theta 0 K and eta recombination plus phi K eta recombination multiplied by JL K eta 0 minus eta recombination. This solution has an intuitive meaning. The photon perturbations don't grow after recombination. The gravitational potential in the universe are too weak to trap photons, and these basically free stream, giving us a snapshot of the universe at the surface of the last scattering. The cosmic microwave background temperature field is controlled by the sum of the kinetic and potential energy, and theta is 0 a K eta recombination plus phi K eta recombination multiplied by is equal to minus delta K eta recombination divided by 6. For example, the temperature of the photons at present day includes the fact that they needed to climb out of the potentials they were in at the time of recombination. Furthermore, the perturbations in this total energy of the photons is controlled by the dark matter perturbations theta with a negative sign, as hotter regions now correspond to underdense regions in dark matter fluid at the time of recombination. The spherical Basel function JL K eta 0 minus eta recombination just encodes how much anisotropy there is on angular scales 1 divided by L from a pure plane wave with wave number k. For large L, JLx tends to x divided by L to the power of L minus 1 divided by 2 divided by L, and thus this gives the relevant contributions to cosmic microwave background anisotropies only for L is almost equal to k eta 0, and eta recombination can be neglected since eta 0 is too much larger than or greater than eta recombination. One last formal step is needed to make contact with the Cl featured in the cosmic microwave background power spectrum and mentioned at the beginning. One can show that explicitly CL is equal to 2 divided by P. The integral lower boundary is 0, upper boundary is infinite dk, the cos power of 2 pk and absolute theta L k divided by delta k to the power of 2, where pk is the matter power spectrum and delta the matter perturbations. This substantiates the qualitative statements that the CLs are the averages of the square of the theta Ls provided by the equation 1.33 in terms of the theta zero at the time of recombination in turn determined by the considerations in the tight coupling regime equation 1.13. The equation 1.33 is approximate and some corrections are important. The missing dipole contribution is smaller and out of phase with the monopole, including it gives higher truths in absolute theta L to the power of 2, which give the CL as just seen, and thus the peaks become less pronounced. The time dependence of the gravitational potential enhances the CL at low L up to around the first peak at the L is almost equal to 200 and so-called integrated Sachs-Wolf's effect. It reflects the fact that the energy density stored in radiation is not entirely negligible at the time of recombination. Finally, the photon diffusion results in damping of all high is equal to L modes. A photon undergoes a random bulk when it scatters on a sea of electrons and therefore diffuses by a comoving distance. Lambda d is almost equal to 1 divided by r square root Ne sigma theta h during the Hubble time h, or distances smaller than the lambda d. The photons restore the temperature of the baryon photon fluid to a single mean temperature, erasing any anisotropies. This effect roughly amounts to A is almost equal to exponential minus lambda d to the power of 2 cot to the power of the superposition of the solution in equation 1.33, visibly suppressing anisotropies for chi eta is 0 is larger than 500. The above simplified analysis cannot capture all the complexity of the real universe, but the main message is clear. The relative heights of two neighboring peaks in the cosmic microwave background power spectrum, in particular the second and the third peaks, carry information about the abundance of the kind of the matter that was coupled by electromagnetism to photons, baryons, which provide the term with R, and the abundance of the matter that provides gravitational forcing field. The latter turns out to be much larger than the former, providing a conclusive evidence for the existence of dark matter. If the universe contained baryonic matter, only the third peak would be suppressed, as shown in the bottom left plot of Figure 1.5 in the disagreement with the data. Now I want to go to the next chapter 1.3.4 Cosmological Bounds on Dark Matter Properties. As we saw in section 1.3.1 and 1.3.3, the large scale structure LSS and cosmic microwave background data allow to test the dark matter behavior. Global fits prefer the simplest model of the cold, non-interacting dark matter with Gaussian adiabatic perturbations. Blue, we summarize what this means and present the current bounds. One can modify the Boltzmann equations for the cosmological perturbation in section 1.3.1 and 1.3.3, replacing dark matter with a more complicated dark fluid with non-zero sound speed, nu-s, making dark matter not cold, and or viscosity, making dark matter interacting. And our modified equation of state W is equal to delta divided by rho density is not equal to 0, making dark matter no longer behaves as non-relativistic matter. Global fits to cosmic microwave background data give bounds at the few 10 to the power of minus 3 level on these parameters based on the reference 29 concerning adiabaticity. Boltzmann equations in section 1.3.3 have to be solved for each component and for any scale called starting from initial conditions at the time much before the matter radiation equality. Cosmic microwave background data are well fitted assuming adiabatic initial conditions, one pyramidal in homogeneity common to all components. Delta K is equal to delta BK is equal to the 3 theta 0 car is equal to 3 n 0 car. The factor 3 for photons and neutrons arises just because theta 0 and n 0 are defined as inhomogeneities in the temperature rather than in the density. Equation 1.35. These equations above means that the density of each component is proportional to the total density so that the overall effect can be described by geometric pyramidal curvatures or equivalently by the gravitational potential. Such adiabatic initial conditions arise in minimal inflations models where all pyramidal inhomogeneities are generated by quantum fluctuation of one inflation scalar field. As usual, quantum mechanism provides predictions for the statistical distributions of these fluctuations rather than specific outcomes of individual measurements. That is why all the observables are averaged over space or equivalently over the Fourier modes with different orientations. Concerning Gaussianity, in section 1.3.1 and 1.33, we focus on the simplest two-point correlation functions IALM. I L amperine is equal to delta L amperine delta M amperine CL in section 1.3.13 and the delta Kapparin is equal to 2p to the power of 3 p Ka and delta to the power 3 multiplied by Ka minus Kapparin in section 1.3.1. The reason is that the quantum fluctuations of a free scalar field with the negligible interactions such as the inflation with its quasi-flat potential flow a Gaussian distribution. Since this is the ground state of a free harmonic oscillator, Gaussian primordial inhomogeneities, on the other hand, are fully determined by the two-point correlation functions compactly described by a single power spectrum. Gaussian inhomogeneities with the cosmic microwave background and LSS data. However, this is not the only possibility. The inflation could have interactions resulting in non-Gaussianities in the probability distribution for the curvature perturbations at zeta, and the phi zeta is absolute almost equal to exponentials minus zeta to the power of 2 divided by 2 zeta to the power 2 minus zeta to the power 3 zeta to the power 3 divided by the parentheses zeta to the power 2 to the power 3 and etc. is equal to, after simplification, exponentially the bracket minus zeta to the power of 2 divided by 2 zeta to the power of 2 multiplied by 1 plus fn zeta and etc. where the variety of non-vanishing three-point functions is loosely characterized by f and l is almost equal to zeta to the power of 3 divided by zeta to the power of 2 to the power of 2 parameter. Single field inflation can be reproduced the data assuming a nearly flat inflation potential corresponding to a small slow roll parameter when the epsilon is almost equal to 0.01, so that the nearly non-interacting inflation produces the PA zeta is almost equal to zeta to the power 2 is equal to H inflation to the power 2 divided by MPI to the power 2, and that epsilon and a small fnl is almost equal to epsilon. This is much blue current bounds on non-Gaussianities implied by the cosmic microwave background data. FNL is less than the 10 to the power of 1 minus 2 future cosmic microwave background and large-scale structured data can improve the sensitivity to FNL by 1 and 2 orders of magnitude respectively. Even lower values can maybe probed by a futuristic 21 centimeter observation, still it remains difficult to devise non-minimal inflationary models that provide signals in FNL. Returning to the issue of adiabaticity in the inflationary context, the extra inhomogeneities can arise, for example, from independent quantum fluctuations of some other fields which happen to be light enough during the inflationary period. From a phenomenological point of view, it is convenient to consider the so-called isocurvature fluctuations. These violate equation 1.35 by ascribing different inhomogeneities to different species, but without affecting the inhomogeneity in the total energy density and thereby in the curvature. We are interested in isocurvature fluctuations in the primordial dark matter density. Delta isometry K is equal to delta rho K dark matter divided by rho the dark matter corresponding to the power spectrum. Delta isotropy to the power of 2 is equal to K to the power 3 Pa isotropy divided by 2p to the power 2. The fluctuation in dark matter density on scales 1 divided by K would then differ from those in the Sm particles. Global feeds to Planck data demand that adiabatic fluctuations are dominant. P K divided by P K plus P adiabatic K is less than 0.038 at 95% Cl at K is equal to 0.05 based on the MPC. The bound applies to fluctuation on scales 1 divided by K that in turn the horizon around matter radiation equality such that the delta adiabatic to the power of 2 is equal to 2.2 and 10 to the power of minus 9 is well probed by the cosmic microwave background. Isocurvature fluctuations are smaller subcosmological scales are understated, for example, the galactic scales. Loosely speaking, the fact that the dark matter has the same fluctuations as normal matter suggests some early connection between the two and restricts the viable dark matter production mechanisms. See the discussion in the chapter 3. So far, we assume that the dark matter is non-interacting. If some extra interaction other than gravity acts on dark matter particles, then equation 1.22, which describes the gravitational clustering of dark matter, gets modified. If the dark matter interacts with neutrons, this generally suppresses the dark matter primordial density fluctuation through collisional damping and therefore leaves noticeable signatures in the cosmic microwave background isotropic power spectra and in the matter power spectra. A rough summary is that the current data constraint the dark matter divided by nu interaction cross-section to be sigma dark matter divided by nu is less than the 10 to the power of minus 32 m per giga-electron volt square centimeter. Assuming absence of temperature dependence, with different studies finding an order of magnitude weaker or stronger bonds. Similarly, the possibility that the dark matter interacts with photons remains viable as long as the interaction is sufficiently weak. The phenomenological consequences are similar to the case of interactions with neutrons. The two first approximation neutrons and photons are simply two forms of radiation at the time of cosmic microwave background. A rough summary is gained that current data constraint to the dark matter divided by gamma interaction cross-section to be sigma dark matter divided by gamma is less than a few 10 to the power minus 33 m per giga-electron volt square centimeter, assuming there is no temperature dependence. There is no particularly constraining in the case where interactions with photons are due to the dark matter carrying a small electric charge. Significantly stronger constraints do exist and are discussed in section 3.1 1.3.2. Another possibility in an extra long-range force acting on dark matter, either only on dark matter or possibly also on other fields. Such a force could arise, for example, if dark matter coops to an extra-scalar with ultralight sub-Hubble mass. Global fields constrain the range of such a speculative dark force to be more than 100 times weaker than the gravity. Now I want to go to another amazing chapter 1.3.5, which is about Big Bang and nucleosynthesis, the determination of the density of normal matter obtained from the global feeds to the cosmic microwave background data. Omega B h to the power of 2 on page 16 agrees with the independent precision determination derived from the Big Bang nucleosynthesis, or BBN. Big Bang nucleosynthesis is a theoretical framework which describes the synthesis of light elements in the universe, the bulk of D and helium-4 and a good portion of helium-3 and lithium-7, the rest being produced later in astrophysical mechanisms such as stellar synthesis and cosmic ray spllations. Starting from their building blocks, the free protons and neutrons present in the primordial plasma. More precisely, the Big Bang nucleosynthesis is sensitive to the baryon-to-photon ratio. Eta is equal to NAB divided by Na gamma because photons break nuclei, delaying their formation temperature. The measurements give this equation. Eta is equal to 6.2 positive negative 0.4 10 to the power minus 10, which concludes the omega pH to power of 2 is equal to 0.022 positive negative 0.002. In agreement with the cosmic background value omega pH to power of 2 and pH 16 to derive the second relation above, we used omega b is equal to rho b divided by rho critical is equal to eta n gamma to the power of 0 mab divided by rho critical, where map is the proton mass and gamma to the power of 0 the present photon number density. The concordance between the two determinations of the boron density is seen as a major success of the standard model of cosmology, giving confidence that the evolution of the universe is well understood within this model. The Big Bang nucleosynthesis probes an earlier phase of the universe than the cosmic microwave background does. For example, for significantly larger temperature T based on the mega-electron volt compared to the T electron volt for cosmic microwave background. The fact that omega B in 1.38 satisfies the omega B is less than omega matter is equal to 0.3, where omega matter includes all forms of matter, provides further evidence for dark matter. This is required to behave as a non-baryonic matter and is needed for the structure formation as discussed in section 1.3.1. The result from Big Bang nucleosynthesis in 1.38 has been especially important historically. Before the cosmic microwave background and LSS measurements became precise enough to be able to pin down by themselves the relative proportions of baryon and dark matter. Now I want to go to the next chapter where dark matter distribution, the galaxy and the universe. As discussed in chapter 1, the average dark matter density in the universe is non-zero. See equation 1.1. However, there is a much more to dark matter than just this average value. Because of structure formation, the distribution of dark matter in specific systems differs significantly from the average cosmological value. In particular, in order to interpret the results of direct and indirect dark matter detection searches discussed in chapter 5 and 6, one needs the dark matter density distribution rho x and the dark matter speed distribution fx nu in the Milky Way as well as in other galaxies in a variety of other astrophysical systems. Presently, only educated guesses are available for these quantities, with significant uncertainties. In this chapter, we discuss the methods with which such guesses are derived and the results. We start with two general statements which are simple, yet at the same time also quite powerful. Dark matter tends to be roughly spherical distributed in gravitational bound systems. The initial conditions in the structure formation generally predict nearly spherical distribution. Normal baryonic matter then collapses in the gravitational well, during which it dissipates energy and cools down, resulting in the spinning disks exhibited by many galaxies. See section 2.4. Unless dark matter has similarly large scattering cross sections, it has negligible interactions and thereby negligible dissipation, neglecting the gravitational effects of the visible matter. Dark matter therefore conserves a spherical distribution so that one can reasonably assume that the dark matter density ρr in astrophysical systems is, to a good approximation, a function of only the radial coordinates, or deviations from this rough approximation are discussed in detail in section 2.4. Dark matter is non-relativistic in most systems of interest. For instance, dark matter particles bound to our galaxy must have a velocity below the escape velocity. Nu escape velocity is equal to 500 km per second. Similar considerations hold for other systems such as dwarf galaxies, galaxy clusters, and etc. with the appropriate nu or the velocity for escapes. Going beyond the above general statements, a rho density of R and Fnu for any given system could in principle be determined in three conceptually independent ways. The first is observationally, by precise retracing stellar kinematics in a galaxy or galactic kinematics in a cluster, inferring the underlying gravitational potential and thereby the density and velocity distribution of matter responsible for the observed motion of the tracers. B. Via theoretical methods describing semi-analytically the process of gravitational collapse and its end result. C. With n-body numerical simulations. We have a footnote which is about the first phrase here, and it says something. This is the systems of interest. This is a non-relative. We are talking about that dark matter is non-relative. This is most system of interest, and a notable exception of dark matter particles in close proximity of dense massive bodies such as a neutron star. In such cases, dark matter particles acquire relativistic speeds and can even transfer their large kinetic energy to the star. See there, for example, section 6.10.4. In practice, A is too imprecise to provide the full ROR, but it helps in determining the local dark matter density, and the B section faces formal and technical difficulties due to the nonlinear nature of the problem and due to the presence of baryonic physics, yet it provides valuable insights into the complex processes involved. Therefore, the current most popular approach relies mostly on C with an admixture of other strategies. Usually, this is a two-step procedure. Guess the functional forms of ρr and fnu in the terms of minimal number of free parameters on the basis of the most often simulations or theory or observations. The second one is determine the free parameters in terms of solid observations of dark matter in our galaxy or in other galaxies. We will present the results of this procedure in section 2.2 and 2.3 for the density and speed distributions respectively. Finally, in section 2.4, we discuss how things can be further refined, going beyond the dark spherical cow limit. Before doing that, however, it is worth elaborating on the three methods mentioned above. Now I want to talk about the methods to determine the dark matter distributions. The first method is observation. I discussed in section 1.1.1 the basic observation that the galactic rotation curves flatten allows to infer the root area is almost equal to 1 divided by r to the power of 2 at larger radius r where dark matter dominates. One can use the same idea to try to extract a row or also at smaller or objects in circular orbits around the galactic center are essentially tracers of the total gravitational potential, hence the distribution of matter. The mismatch between the rotation curve obtained with the such tracers and the one expected from the visible matter in the galaxy must be accounted for dark matter. The dark matter density distribution can thus be obtained by fitting an appropriately parameterized function to the total rotation curve based on the equation 34. This is often referred to as the global method to determine the dark matter distribution as opposed to the local method discussed below, which is less ambitious and only aims to determine the dark matter density at the location of the solar systems and about 1 kpc around it. The method is conceptually simple to obtain the predictions of the rotation curves, the Poisson equation for the Newtonian potential field, the delta to the power of 2 phi is equal to 4 pi g rho is first solved assuming as source only the observed mass distributions due to baryons in the stars and from those in the interstellar gas. Rho is equal to rho B is equal to rho star plus rho gas, taking into account their approximate cylindrical rather than spherical geometry, or the theta, the Newton's equation for a test mass in a gravitational field. Nu to the power 2 divided by r is equal to minus delta phi divided by delta r, or it is the partial derivation. Then predicts the rotation velocity nu r is equal to nu s to the power 2 nu plus nu gas to the power of 2 and the whole of this parentheses to the power of 1 divided by 2 in the galactic plane at the 0 is equal to z is equal to 0 where these are measured. Comparison with the data for NUAR shows that an extra dot contribution is needed in order to reproduce the observations. Nu to the power 2 is equal to nu s to the power 2 plus nu x to the power 2 plus nu dot to the power 2, which then allows to determine the dark matter contribution by subtracting the predictions from the observations. However, a number of difficulties arise where solar kinematical data still carries significant uncertainties, both intrinsic to the measurements and due to their interpretation. Also in the Milky Way, related, for example, to the knowledge of the precise distance of the Sun from the galaxy center and of the Sun's circular velocity. Second, the results of the mismatch field mentioned above depends crucially on what is being assumed for the visible component of the galaxy. More precisely, one has to design a model of the galaxy as a system composed of blues, a possible bar, a disk, a gas halo, and possibly even a smaller disk at the core of the blues. Each of these appropriately modeled using several observation-based configurations. The gas density is extracted, for example, from the 31 centimeter maps, which the Staller models are needed to convert observed luminosity into mass density. The uncertainties on these baryonic morphologies are still sizable despite the recent improvements due to the fact that data mostly based on optical observations are now being replaced by the near-infrared data, which need only minor modeling corrections. Finally, since the baryonic matter dominates the gravitational potential in the inner few kpc of galaxies, the inner almost is equal to 5 kpc for the Milky Way, the contribution of dark matter is intrinsically very difficult to determine in the region. In practice, therefore, observational methods are sufficient to affirm the presence of dark matter in galaxies and to get a rough idea of its large-scale distribution, but are at present not sufficient for more precise determinations. The next is gravitational collapse of collision-less dark matter. But before that, I want to review the footnotes here. Galaxy refers to both Milky Way as well as to any other galaxy, including the satellites of the Milky Way, for which one is trying to determine the dark matter distribution. The next footnote is talking about the velocities orthogonal to the galactic plane, and the radial velocities provide extra information in principle. In practice, however, they are not measured well enough. Now, the second method is gravitational collapse of collision-less dark matter. The formation of a dark matter galactic halo is a conceptually well-defined theoretical problem. Start from a roughly spherical slide or density made of collision-less and dissipation-less bodies and let it evolve under gravity. The system starts collapsing under its own weight, and at some point the inhomogeneity grows beyond the computable linear approximation, but the collapse self-limits without reaching a point with infinite density. This happens because dark matter is collision-less and cannot dissipate energy. So during the collapse, its gravitational potential energy has to be converted into kinetic energy of the dark matter particles involved. The sphere therefore eventually relaxes to a self-gravitating quasi-static structure supported by random motion of dark matter particles. The whole process is referred to as uh, viralization structure, and the resulting system is viralized. For example, its energy is distributed between the potential energy V and kinetic energy K according to the viral theorem. K is equal to minus 1 divided by 2 V, already mentioned in section. The Borel theorem provides enough information to estimate typical scale involved. For simplicity, we consider spherical dark matter or density with homogeneous density of total mass and total ellipsoidal collapse models with non-constant density are also considered in the literature. The main phases discussed below are illustrated in Figure 2.1. We define rho as the homogeneous density at the instance of turnaround. For example, at the moment at which the ore density stops following the expansion caused by the Big Bang, stalls and turns around to start collapsing into the gravitationally bound objects. This marks the onset of structure formation. Since dark matter is stalling, its kinetic energy eta vanishes, and thus its total energy eta is equal to eta plus v eta, and is entirely due to the gravitational potential energy. V eta is equal to minus g. The integral lower boundary is 0 and the upper boundary is RT is multiplying by 4p r to the power of 3 divided by 3 rho in multiplied by 4p r to the power of 2 dr p rho tr divided by r is equal to minus 3 divided by 5 gm total to the power of 2 divided by r total, where rta is the size of the sphere or at torn around, and rho in is the density inside the sphere. In our approximation, take an account equal to the rho top. If spherical symmetry were absolutely exact, for example, if all dark matter particles were following a perfect radial trajectory, the collapse would have proceeded toward infinite density, forming a black hole. In reality, the system keeps spherically only on average and reaches a finite density thanks to the chaotic motion of dark matter particles interacting only via gravity. After this volatilization process, the energy is distributed between the kinetic and potential energies such that the E violation is equal to E chiviral plus V viral is equal to V viral divided by 2, where the last equality follows from the viral theorem. Since volatilization conserves the total Energy, the potential energy V overall is equal to minus 3 gm total to the power of 2 divided by 5 R overall. We still approximate the density as constant. Rho V overall is equal to mx total divided by 4 divided by 3 P R overall to the power 2, where now R overall is the radius of the volatilized halo, therefore implies the R overall or radius overall is equal to R tie divided by 2. That is, the collapse results in a relaxed halo half the size of the turnaround bubble with an order of magnitude higher density. Rho is equal to 8 rho eta. The mean square speed a volatilization particle is nu to the power of 2 is equal to 2 chi viral divided by m total is equal to absolute V viral divided by m total is equal to 3 G m total divided by 5 R viral. Solving Newton equations for the homogeneous density in an expanding matter-dominated universe shows that the average density of a form halo rho is roughly 200 times the surrounding cosmological density. So thank you so much for watching my tutorial video until the end. Today is the 16th of the August, and if there's any simulations for this literature, you can find it from my github.com/masterscript/Cauchy script and /Safra script.